in a way what you want, because it's a bit of both, actually. And we take it up here because it links nicely to this whole example. The example have, in a way, the standard deviation part of the example did this for us. Even though I put it in a terrible math expression here, I say, generally speaking, if we generalize that functions that we meet later in our lives will not all be x times y, the area. Functions could come generally complicated and as functions of more than two things, of potentially many things. And complicated nonlinear functions could hit us in the systems that we work with as an engineer. So this is the general expression. This is kind of function of x and y. Could be the area, but also could also be more general. What we need to be able to actually to deal with errors or an uncertainty, we need to know the variance or the sampling variance of our computed feature. So I'm just trying to put the math expression, linking it to the kind of expressions we've seen in the course. This is, in fact, the important challenge for us, corresponding to finding the standard deviation of the area computation from before. Of course, also the probability distribution, fine, that's more general, but let's focus on the noise, on the error. This propagation of error thought is a term, is something that you could have or would have already met in maybe a physics class or a chemistry class or a chemistry book or physics books, talking about how uncertainties, how errors on measurements might propagate through nonlinear computations that you do based on your physics or chemistry formulas that we are using. Actually, we've done something like this already, but in a simplified setting. When this function that we are computing, in fact, if this function is linear in the inputs, right? Can you remember the airline example? You do, with 55 passengers. We had the rules for computing means and variance for linear combinations. This is the rule. I've restated that rule here, just to make the link. When the function is linear, we've already done it. Fine, we know it. Then we can compute the variance of a function, of a linear function of the inputs. But already then, and now we know for sure that we cannot cope, we cannot just deal with linear functions. It's much too restricted. Nonlinear functions already hit you many years ago, and as an engineer, it hits you every day, right? Because you work with real-life phenomena, and real-life phenomena are nonlinear in nature, by nature, most of them. So we need to think about nonlinear structures. And the probability tools that we otherwise teach you in this course are too limited for that. However, here is a classical, the nonlinear error propagation law. The independent version of it, the simplest version of it, comes here. It tells us, and you have to learn how to use this one. It tells us how to find the variance or the error or the uncertainty, if you want, of the function, nonlinear function of multiple inputs. It is a formula that looks very much like the simple linear formula we've already seen. Here it was, sorry. Here's the simple linear formula, where we sum up the variances coming from each individual input times the factor that enters the linear combination. Now, it's the same thing, that we sum up the various variances coming from the different inputs, but the factor we are going to multiply with is more complicated. It's coming from a Taylor approximation of the nonlinear function, if you want. However, you need to find the derivatives of the original nonlinear function with respect to each individual variable. Hey, whoa. We actually need our math tools to be working as engineers. We need to be able to do derivatives of a nonlinear function to be able to get the uncertainty of what we do, the variability. Do you remember how to find derivatives of functions? Well, you know where you can go back and find out if you don't remember. Let's see how it works out in practice. In our example with the area. So the function is this function, right? And this is how actually I would say small x here, but anyway. This is quite, you have to get used to how to use this, and it's easy to be confused here. I accept that, because also the way people talk about this in physics and chemistry, we have to get used to how it links with how we talk about it here. However, here's one way that it could be used. What if you were given two specific measurements? And for now, I just assume these measurements are 2 meters and 3 meters exactly, not to put any other complications into it. Then you could ask, what would the uncertainty typically be on the area, on a single area measurement? For instance, exactly the one we have done. You, like in a physics report, you report the result to be 6 on the area in your experiment. But what is the uncertainty about this number 6? If you should report that one also, right? That's a variance you're asked to report in such a physics report. How do I compute the variance of an area? Well, when I know the variance of the length and the width, I can compute, at least approximative, the variance for the area by the error propagation law. Here it comes. I know by the settings of the little exercise or the little story that the variance, one of the variances was this, the other variance was this. So now I know 2 of the sigmas in my error propagation. Now I just need the factors coming from the derivatives. The function is a simple one. The derivative of this function with respect to x, that's just a constant, that's y. The derivative of the same function with respect to y, that's just the x, right? I hope you remember this basic rule for how to find derivatives of k times x, that's k, and that's I've used that twice, one for x and one for y, the same rule, right? Now I've done the derivatives. Now I use those to plug into the formula. The formula is restated here. That is the square of the derivative and square of the other derivative in the formula. Expressed again here. And now I plug in the only values I have to plug in this example. I plug in the y value and I plug in the variance. I plug in the x value and I plug in the variance. And my approximate, because I emphasize the nonlinear error propagation rule is approximating the variance, because it's like linearize, making the function linear by a Taylor approximation, and then using that as an approximate variance for the stuff. So this is the variance, which matches pretty well with our standard deviation of 0.05, actually, that we found in the simulation, right? Here's the first one of a number of terrible slides and method boxes in this chapter 4. All of the method boxes, apart from we have the nonlinear error propagation theorem that I just told you. That's an explicit formula that you can use, like we've been used to. It's a little math formula, we can use it. All of the rest of the formulas describing, or method boxes, describing the simulation tools that I give you, looks like this. And tries to make explicit the procedures that we need to use in R, because we cannot do this without a tool like R. It's based on computer use, right? So basically just telling how to make the computer find the result for us. Not by an explicit formula, but by a procedure. right? Combined with a bit of explicit formula also. But basically the procedure is simulate k outcomes. Maybe I should emphasize that I'm giving you now, as a general method, a simulation version of the same thing, which I have already applied in my example, right? This is just putting into formal procedure what I showed you already previously in the example. How did I find the standard deviation of the areas? In the example, well, I simulated 10,000 outcomes of all of these measurements from different normal distributions, one for the length, one for the width, right? And then there could be x3, x4, x5, x6. There could be many of those. It doesn't have to be only two. Then I basically just compute the standard deviation on those values coming out of it, right? I compute all the values. I plug in all the x1, x2, x3, x4 in the f. I compute the 10,000 f's, and I compute the standard deviation on those 10,000 f's. Dangerous up here. And that's it. So this is the formal procedure version of what I just did in the example. Error propagation by simulation. This is nice. Why don't we spend a couple of days on trying to learn how to go through this mathematical proof? Not so. 30 seconds. I'm just showing it to you to show you that it can be done, because I haven't shared the rules with you all in all detail that can make us do this. What I've shown on this slide is what I summarize here, that by this last slide that I only showed you in 30 seconds, I showed you the theoretical derivation of the real variance of the nonlinear x times y. That can be done actually in this case. You couldn't do it with the tools I've taught you. With a day extra, I could teach you how to. It's not rocket science, but I would need a lecture or so to teach you how to be up and running with such a derivation like this one. So, of course, I could teach you if I wanted to spend the time. I bring it here to make you think like this. When I'm trying to get to, practically, what is the noise for the area here? I have now shown you 3 different approaches. The last one is the most mathematically complicated. Maybe I could theoretically derive the right variance from theory. Or maybe I could use still an analytical explicit formula expression given by this error propagation rule with the derivatives. If I can find the derivatives, then I can manage to use the formula, right? That's an approximate version of an explicit thing. Or what I actually started out with in the beginning, before even talking about the rule, but just showing you how to do it, is I could do it by simulation. These are 3 alternatives to solve the same challenge, to get the variability of the area or any other nonlinear function of something. The simulation approach, that's my point, of course, does have a number of crucial advantages for you guys, and for me also, at this point, compared to the other more mathematically theoretical based methods. It can actually make you compute things that you wouldn't in your wildest fantasies dream of being able to handle theoretically. I'm trying to make that point again and again, and I'll get back to it after the break also. It offers a tool, we will see, that maybe, just maybe, we shouldn't base everything on the normal. I mean, my error propagation rule in a way is based on the normal. It doesn't have to be. It could be any other thing. And that's just changing in my simulation procedure. It's very easy. Just write L norm instead of norm, and then it runs. Not a big issue. And in a way, actually, the nice thing about simulation is that it does not rely on this Taylor approximation of the nonlinear function. It's actually truly taking the nonlinear structure into account in the right way. And the only challenge is related to the question asked by the young lady there. We need to be sure that we simulate enough, that we have precision enough that the result is the right thing. That is simulation and error propagation. we are ready for the big thing after the break. Let's do 15 minutes break.